Jnanam paramam dhyayam. Knowledge is supreme.
Welcome to this course on advanced transition metal organometallic chemistry. We have been discussing carbon heteroatom bond forming reaction, and moving on from the carbon heteroatom bond forming reaction, we are going to be discussing some more applications of organometallic catalysis. But before I do that, let me just recapitulate what we have been discussing in the last few lectures. To begin with, we looked at palladium catalyzed CC bond forming reactions, then we went on to move to various types of carbon heteroatom bond forming reaction. In that context, we have looked into carbon nitrogen bond forming reactions, carbon boron, carbon silicon bond forming reactions. Much of these reactions are addition type reactions, and very few of them are sigma bond metathesis type, like cross couplings are type. And in the silylation hydrosilylation reactions, we had seen another interesting reaction, which is a dehydrogenative coupling, in which the silicon silicon bond is formed as a part of this silylation reaction. Now, we are going to focus on some more interesting catalytic applications of these organometallic complexes. In particular, various reactions that we would be looking at are olefin oxidation, Fischer-Tropsch reaction, carbonylation of alcohols, hydrogenation of alkene, alkene hydrogenation, hydroformylation reaction, and this Rapi synthesis. So, these the length and the breadth, the extent of the chemistry demonstrated by this variety of reaction sort of highlights the scope of organometallic complexes in homogeneous catalysis. It sort of again promotes or the utility of organometallic complexes, or dominance of organometallic complexes in the world of homogeneous catalysis can be understood by the scope of reaction, the diverse reaction that these organometallic complexes carry out that currently are used in large scale industrial processes. So, with that we are going to be focusing on the first reaction, which is olefin oxidation reaction. Now, other than the palladium in organometallic chemistry is mainly known for their CC carbon-carbon or carbon heteroatom coupling reactions, but palladium also catalyzes various other redox reactions, and olefin oxidation is one such thing. We are going to be looking at it in bit more detail. So, other than then C and C heteroatom coupling. Palladium also catalyzes various redox reactions. The most important one is the oxidation of ethylene to acetaldehyde. This is an interesting reaction. Is the oxidation of ethylene to acetaldehyde. And this is popularly known as Wacker's process, and it was one of the first homogeneous catalysis with organopalladium chemistry to be successfully applied in industrial scale. So, this is popularly known as Wacker process. Wacker process. One of the first homogeneous catalysis with organopalladium chemistry to successfully applied in industrial scale. So, this Wacker reaction is something that we are going to be looking at in much more detail, and this is a very interesting reaction. This Wacker process consists of multiple elementary steps, including a copper couple, and we are going to looking that in bit more detail. This process is known for over 100 years. It is a pretty old process, involves the oxidation palladium 2 palladium 0 couple and reoxidation of palladium 0 to palladium 2 by oxygen mediated copper 1 copper 2 couple. Involves reoxidation of palladium 0 to palladium 2 by oxygen mediated copper plus copper 2 plus couple makes the reaction catalytic. The elementary steps are given by this equation. First, C2H4 plus PdCl2 plus H2O, CH3 CHO plus Pd plus 2 HCl. Step 2 is Pd plus 2 CuCl2 PdCl2 plus 2 CuCl. Step 3, 2 CuCl plus 2 HCl plus half O2 giving 2 CuCl2 plus H2O. Now, first is acetylene with palladium chloride, keep acetaldehyde plus palladium 0. Next comes the oxidation of palladium 0 to palladium 2 with copper chloride becoming Q plus chloride, and Q plus chloride is further oxidized to copper 2 chloride in presence of oxygen. So, the net reaction is C2H4 plus half O2 giving CH3CHO, and delta H for this reaction is minus 221 kilojoule per mole. So, this is an interesting reaction in which acetylene is converted to acetaldehyde. This is one of the first homogeneous catalytic process that has been used in industrial scale is known, and that the reaction involves the oxidation of acetylene to acetaldehyde, and the process the palladium 2 gets reduced to palladium 0, and the catalytic cycle is completed by reoxidizing palladium 0 to palladium 2 by a copper 2 to copper 1 couple, and then the copper 1 then further gets oxidized to copper 2 in presence of oxygen. So, this is quite an interesting reaction, and we are going to be looking at the catalytic cycle to get an idea as how this reaction works. So, the first involves the reaction of palladium Cl2 is reacting with CH2 plus Cl minus to give this complex PdCl Cl olefin anionic. The next step is water getting added and Cl being eliminated to give this aqua coordinated complex Cl. This is a neutral complex which loses a proton to give a palladium hydroxo species PdCl olefin ClOH. This palladium hydroxo species then reacts with water. So, water goes and attacks and protonates this hydroxo to water, and this olefin becomes CH2OH. So, this gives PdClOH2 CH2OH Cl minus and then this loses chlorine to give PdCl ClOH2, CH2, COH, H, the hydrogen then attacks palladium to give a palladium hydride and an olefin CHOH, CH2, water, chlorine, that undergoes this hydride insertion to give PD OH2 Cl C H CH3 OH that eliminates minus HCl minus water to gives CH3 CHO and palladium 0. Now, this palladium 0 gets converted by 2 Cu Cl2 to 2 Cu Cl, and that goes back with half O2 minus H2O to give 2 HCl. So, this is a complex scheme in which the first the PDC palladium 0 becomes oxidized to palladium 2, then coordination of the olefin, then replacement of the chloride with the water. After the replacement of the chloride with the water loses a proton H minus to give anionic hydroxo species, then water is added to this olefin and this becomes CH2OH, chloride is lost into, so to give Cl, water, CH2 neutral compound, CHOH. Now, the hydride sort of attacks the palladium and the olefin is created, which is this hydrogen goes, this bond breaks to give a olefin coordinated palladium hydride chloride aqua complex. Now, this hydride chloride aqua complex then undergoes this hydride transfer to this olefinic bond to give palladium methyl, and then that eliminates HCl as well as water to give this acetaldehyde and platinum 0, palladium 0. And then once the palladium 0 is formed, then that using this copper 2 copper 3 cycle goes back. So, the interesting there are 3 interesting aspects of this reaction. The first is this formation of this olefinic double bond. The second is the attack of this double bond hydrogen on the methyl, which is the formation of the acetaldehyde, and the first one obviously was the attack of the attack of the water followed by deprotonation to form the palladium hydroxo species. So, this is a complex cycle, and this catalytic cycle produces ethylene to acetaldehyde. These are two, this is the reactant and this is the final product of the reaction, and this has been catalyzed by this organopalladium species. So, this is an interesting demonstration of how the palladium based complex can carry out oxidation of ethylene to acetylene. So, there are steps involved. We are seeing the first one obviously the Logan the chloride being replaced by water, then then there is isomerization, then addition of hydroxide to the double bond in the cis disposition, nucleophilic attacks only when the coordinations fair, beta hydride elimination, insertion, reductive elimination, so on and so forth. So, the regioselective, now the olefin oxidation can also be done in a regioselective fashion, and so that speaks us about the breadth and the scope of this catalytic cycle Walker process. So, let us talk of now regioselective olefin oxidation reaction. So, olefins with 3 or more carbon atoms are oxidized regiospecifically to ketones. Olefins with 3 or more carbon atoms are oxidized regiospecifically to ketones. As a result, terminal alkenes from methyl ketones are formed. So, the terminal alkenes form methyl ketones. And this is illustrated by this example. R plus half oxygen with PdCl2 CuCl giving this methyl ketone. Similarly, propene gives acetone. Similarly, acetone is obtained from propene. Now, here is another chemoselective oxidation of olefin example. So, alkene in presence of aldehyde can also be achieved. Chemoselective olefin oxidation. Selective oxidation of alkene in presence of aldehyde can also be achieved. So, this is illustrated by this beautiful example in which this olefin CHO in presence of half oxygen PdCl2 CuCl in DMF water 25 degree centigrade, giving the oxidation of this olefinic internal methyl ketone CHO in 78% yield. So, this shows that the selective oxidation of olefin to give methyl ketone and this aldehyde remaining untouched. So, this is an example of chemoselective oxidation was observed. We had also seen that this can be performed in a regioselective fashion and also in chemoselective fashion. Another important application of Walker oxidation is that it is not only restricted to aqueous medium. Walker oxidation can also be carried out in non-aqueous solvent. In non-aqueous medium. And this is given by H2C CH2 plus half O2 with PdCl2 CuCl in water, giving acetaldehyde with alcohol, giving HOR vinyl ether and with acetic acid and sodium acetate, it gives CHOAC vinyl acetate. So, this also is an important demonstration that Walker oxidation can be extended beyond aqueous medium, and as a result, depending on the type of solvents that people use, they can produce aldehydes in water, in alcohol, vinyl ether, and then in acetic acid it produces vinyl acetate. So, this is interesting reaction which sort of highlights the scope of this Walker oxidation in non-aqueous medium. So, with this I would like to conclude today's discussion on olefin oxidation reaction. In particular, we have looked at a very industrially important one of the first organometallic examples of organometallic catalysis making it a big way in the industrial scale up processes is this olefin oxidation. Now, to begin with, we had observed that though palladium is primarily known for their CC coupling and cross coupling reactions, the palladium had also been long known for over 100 years for its ability to oxidize ethylene to acetaldehyde, and that too in a very catalytic fashion. So, from that perspective, historical perspective too, Walker oxidation is among the first few examples of organometallic compounds making it big in industrial processes. So, this Walker oxidation requires palladium, but also requires palladium copper 1 copper 2 couple to oxidize back the palladium 0 to palladium 2. Now, this reaction proceeds with multiple elementary steps. The first of all involves the coordination of olefin, then the attack of the water, then beta hydride elimination, finally the hydride migration, followed by the elimination of the acetaldehyde. We had also seen that despite the complexity in mechanism, the reaction is extremely useful in producing value added chemicals like acetaldehyde, which can be used for producing many other commodities. We have seen the Walker oxidation reactions can also be performed in regioselective fashion. Not only that, it can also be performed in chemoselective fashion, in which it can oxidize the olefin in presence of an aldehyde, where the aldehyde remain untouched. And lastly, the Walker oxidation can also be extended to non-aqueous medium, thereby highlighting the scope, the importance of this reaction, and the scope and the breadth of the utility of this oxidation process. So, with this I conclude today's lecture on olefin oxidation, particularly the Walker oxidation process. We are going to be continuing some more discussion on oxidation process, Walker oxidation, as well as we are going to take up other examples of organometallic catalysis. So, I again thank you for patiently listening to me in today's lecture, and I look forward to taking up more on Walker oxidation and subsequent other catalytic examples of organometallic complexes in the next lectures to come. Till then, goodbye and thank you.